Now, let's get back to the first kind of moment we want to introduce, which is called the moment of a force about a point. Okay, so again, going back to look at this original picture, we have a rigid body here in three-dimensional setting. We have a force acting a certain point A. This is a force. Now, what is the moment of this force about point O? So the definition of the moment of a force P about point O is defined as R cross F. So I already introduced cross product. Now I need to talk about this first vector. I need to talk about the second vector in order to demonstrate the result, which is called the moment of a force about that point O. The first vector, R, is the distance vector from the point you want to calculate the moment of, that means point O, to the point the force applies on. Okay, in other words, this R should be from O to A. So you need to keep in mind this R vector is not from A to O. It's from O to A. And O is the point you want to calculate the moment on, and then the point A is the force, is the point the force applied on. Okay, so from O to A, and that's called the distance vector. From the point you're interested in calculating the moment on to the point the force is applied. Okay, so that is R. Cross force vector, F. Because normally when we ask you what is the moment of a force about a point, then of course we need to give you the force first, or you need to calculate the force first. So basically, in order for you to calculate the first kind of moment, which is called the moment of a force about point O, you need to figure out the distance vector, and you also need to figure out the force vector. So all the equations or formulation we had in the previous chapter 2 would work to deal with this force. But this chapter, in addition to this force, you also need to figure out the distance vector. Okay? So, if we want to expand a little bit further to see the moment, then what we can have is from the definition of a cross product between two vectors, then the magnitude of the moment. First of all, this is a cross product, so that the result must be another vector as well. Okay, because the product is a vector if we are doing the cross product. Okay, R cross F, the result should be a vector. When we talk about vector, then we need to talk about two things. Number one, we need to figure out the magnitude, and we need to figure out the directions. Okay, so first of all, what is the magnitude of this moment? So this one is different from here because this is the bolted, or in other words, there's an arrow on top. This one does not have. We call the moment as a magnitude. So the magnitude of the moment obviously equal to the magnitude of this R. What is the magnitude of this R? Well, you just use the same R. This time is now the vector, is a distance between O to A. The distance between O to A is the same distance between A to O. When we talk about distance, whether from this point to another one or from the other one back to the first one, the distance is the same thing. But when we talk about distance vector, they are different. Because distance vector from O to A is different from A to O. So this is the distance we call R. That's the measure between 2 points. Multiply the magnitude of this F. So the magnitude of this force vector, we use F. And then we need to multiply sine theta. Sine theta is the angle between these two vectors. So back to this one, R is a vector from O to A. So then this is a vector. And then the force vector is here. That's why this is the angle between these two vectors. So that's why you have R times F times sine theta. So later on, when I show you more examples, in three-dimensional setting, we do not use this equation to figure out the magnitude. We just use the cross product term by term. However, when you deal with a two-dimensional problem, which I'm going to give you some example as well, for two-dimensional problems, because it's simple, two-dimensional. So that's why sometimes we do use this equation to easily figure out the magnitude. How to do that? If you go back to look at this, R cross F cross sine theta. Now, here is theta, right? Here is theta, the angle between two vectors. This theta is also equal to this theta because these two angles are the same because between these two vectors, right? So then, let me ask you, what is R times sine theta? Let's forget about F for the time being. What is R cross sine theta? what you need to do is to find out the shortest distance from this O to this force line. So this is the force line, this is the point O. You find out the shortest distance. Shortest distance means this angle is 90 degrees. So then from this small triangle, R cross sine theta equal to D. Right? So R cross sine theta equal to D. Then finally you end up with F times D. So F is still the magnitude of the force, but D is the shortest distance from the point you want to calculate the moment to the force line. So this is a force line. And that's called the shortest distance. This equation, the magnitude of the moment equal to F times D, is frequently used for solving two-dimensional problems. In three-dimensional problems, we don't need to use that because there's too much geometry is involved, which is now easy for us to figure out the so-called shortest distance. However, for two-dimensional problem, it's very straightforward. So that's why I would like you to keep in mind many two-dimensional problems. When we calculate the moment or the magnitude, we just simply use F times D. So we're going to use this F times D term from this chapter all the way to chapter 8, in fact, for most two-dimensional problems, because that's a very straightforward way to calculate the magnitude of the moment. Okay? But for three-dimensional problem, we don't use this equation. Okay? So first of all, we figure out the magnitude, but what's the direction? The direction follows the right-hand rule, right? So when you have R this, when you have R and you have F, use the right-hand rule, then the result of the moment should be perpendicular to this plane, including these two vectors. That's why you look at this kind of wide plane, then the moment should be perpendicular. Okay? So for many two-dimensional problems, you need to use this equation, and you also need to use the direction of the moment which is perpendicular to that plane. But again, for three-dimensional problem, we always use this fundamental equation. Okay? So I'm going to show you more examples for two-dimensional problem and also three-dimensional problem. Okay, so now let's talk about two-dimensional problem first. Moment of a force about a given point under two-dimensional situations. Okay? Let's say we have a force on this two-dimensional rigid body. So this time we basically just plot a thin plate instead of general three-dimensional object, right? So let's say in this two-dimensional thin plate, there is a force acting on this point. There's a force acting on this point, but must be in this plane. Otherwise, it's not called two-dimensional problem. So we first identify there is a plane, like the XY plane, for example, and then this force must be acting at some point, but it's in that plane. That's called two-dimensional problem. If I have a force acting on somewhere out of the plane, that's three-dimensional problem, which I'm not talking about right now. So if there's a force acting at a certain point in this plane, then one question is, what is the moment of this force about another point O? And this point O must be also in that plane in order to be called two-dimensional problem. Okay? So what is the moment of this force about another point O? Obviously, you can follow this equation, which is R cross F. So R is a distance vector, but you only have two components because it's a two-dimensional problem. There's no z components. And F is also a vector, but it only has x and y component. There may not be a z component. You can figure out R, figure out F, and do the cross product with the definition we gave you before. However, for most two-dimensional problems, we're not going to use that equation. Instead, we're going to use this one to characterize the magnitude. And then we're going to use the right-hand rule to characterize the direction. Okay? But I'm not saying you have to use this. You can use the original definition. That's why sometimes you need to know both of them. Okay, first of all, let's figure out the magnitude of this moment of this force about point O. What's the magnitude? Magnitude is called F times D. What is F? The magnitude of this F, which is called this F. This is F without an arrow on top. That's the magnitude of this F times D. What's a D? For two-dimensional problem, again, D is called the shortest distance from the point you want to calculate the moment to the force line. So this is the force line. So this is a force line. What's the shorter distance? That's a shorter distance with a right angle here. That's called d. So then you have F times d to indicate the magnitude of that moment. Number one. Number two, we need to figure out the direction. What's the direction? You can follow the original definition saying, oh, yes, the direction is perpendicular to this plane. That's nothing wrong, but actually this time we're talking about a simplified way, which is called clockwise or counterclockwise. So the sign convention in this book, and actually in most of those statics books, even including those college physics books, normally counterclockwise serve as positive. Okay? So now, if you are holding this point, so this force, the moment of this force about the point O is to have some kind of rotation potential, right? In a counterclockwise way. So if you figure out this moment is a counterclockwise, because that's right-hand rule, right? So then you put a positive sign in front of the magnitude. The magnitude itself is always positive. But you just put another positive sign. So this one indicates the direction of the moment, because it's a counterclockwise. And by definition, counterclockwise is positive. Okay? So that is the moment of a force about the point in our two-dimensional setting. You may say, well, how about another scenario? Again, we are having a two-dimensional thin plate, for example, and there is a force acting on this point. Now, what is the moment of this force about another point O? Same thing. Number one, we need to figure out the magnitude of this moment, which is F times d. Same thing, because every time we use this F times d in two-dimensional problems. So what is F? That's the magnitude of this force vector. You can figure out the magnitude and multiply d, which is the shorter distance, from this point to the force line. So this is the force line. From this point to the force line, that's a shorter distance with a 90 degree. That's called d. F times d. Together form the magnitude of the moment. Now, second, we need to find out the direction. The direction this time, when you have R cross this F, use right-hand rule, that's going to be clockwise. If clockwise, by sign convention or definition, is negative. So you put a negative sign in front of the magnitude, indicate it's always clockwise. But let me tell you, either this or this is only for two-dimensional problem. Okay, so in three-dimensional problem, do not use this. Sometimes, even for two-dimensional problems, you may not use this. The reason is, many times, or at least sometimes, it's not easy to figure out d. Okay, so think about it. If you find a way to figure out the short distance, go ahead to use these two equations, because this is the easiest way to deal with a two-dimensional moment problem. But sometimes, when you have a problem identifying d, then my suggestion is still go back to use this fundamental equation. And this will always give you the correct answer without touching on what we call short distance. If you, for whatever reason, you cannot figure out the short distance. Whether it's two-dimensional or three-dimensional, it doesn't matter. Okay? So for three-dimensional problems, I don't want to talk about this at all. In fact, I always use this equation because I don't want to deal with so-called short distance from the point to the force line, but it is in a three-dimensional setting. It's very complex, okay, in order to figure out the short distance. But for some two-dimensional problems, it may be a good idea to use this equation to easily figure out the magnitude of the moment, if we can easily find out the short distance. Okay? Back to three-dimensional, that's what I said. We never use these two scenarios to deal with three-dimensional, but there's many problems, in fact, are three-dimensional in nature. If that's the case, that's the only equation you need to use to calculate the moment of a force about a certain point, right? For example, again, back to this three-dimensional setting, we have a force acting on this point A, okay? This time they didn't plot a force, instead they gave you three components, that's fine. There's a force acting on point A. What is the moment of this force about point O? Okay, by definition, R cross F. What we need to do is to identify three components of this R, which are X, Y, and Z, by looking at this picture. So this is original point, point A, you have 3 components, then R is from O to A. So obviously you have 3 components x, y, z. So that's why you get R vector. And what is the force vector? The force vector, basically the 3 components of the force, which are given here, and then you write like this way to indicate this a force vector in 3-dimensional setting. Now we are dealing with R cross F. Okay, so remember I was introducing the fundamental equation to deal with the cross product between vector P and vector Q. You can go ahead to use this cross product by yourself, or you can use this one. Either way. Now, let's say we use the determinant. No problem. The first row, the 3 components are always I, J, K. Always I, J, K. And don't forget the arrow on top, because these I, J, Ks are the vectors. The second row, 3 components, the 3 components of the second row are the 3 components of the first vector R. The first vector R is x, y, z. That's right here. And the third row should have the 3 components of the force vector, this. And then you just do the cross product, or you do the determinant, you finally end up with this one. Okay? So this is the final result, or you can deal it by yourself. But of course, you may say, well, this is so special because you are talking about the moment at the original point. How about we talk about moment at any other point rather than the original point? There's no problem. Let me give you a more general case. So this is the more general case. Now we're not talking about point O. We're talking about the force acting on point A. Then what is the moment of this force at point B? Right? This B is an arbitrary point. So how to deal with the calculation of the moment? This again is R vector cross F. But this time you just need to figure out R vector. So again, what is the R vector? Distance vector. From the point you want to calculate the moment of, that's point B, to the point the force applied on. So that's going to be from B to A. When we talk about from B to A, that means what? Later on you need to use A subtract B. It's not B subtract A. From B to A, that's called the distance vector. So then you're going to figure out the 3 components of point A. You're going to figure out the 3 components of point B and use A subtract B. So A subtract B, you finally end up with this. These are the 3 components. So RA minus RB. In other words, this is the 3 components of point A. You have XA, YA, ZA, minus 3 components of point B. That's XB, YB, ZB. All together form this vector, which is called the distance vector. Again, from B to A, that means you A subtract B. In general, I don't like to use this kind of a symbol, saying A slash B. It seems to me it's kind of confusing, but if you can figure out if A slash B means A subtract B, that's fine. But normally what I would like to say is, I basically say R from B to A. Let's say B and then towards A. That means I know is A minus B. So this is the bottom line. 3 components of point A minus 3 components of point B. And that's the distance vector. Back to this. Second, what is the force vector? That's always the same thing. You go back to look at chapter 2, right? The force vector, which can be written like this. Then you need to calculate the moment with a cross product. Again, the first row are always 3 components of unit vectors I, J, K. And then the second row should include the 3 components of distance vector, followed by the 3 components of a force vector in the third row. And now you need to calculate the determinant of this 3 by 3 matrix. So again, do not just leave like this. This is not the final answer. This is a formula equation to show you for how you're going to finally end up with something. But just do not write here. Do not write like this. This is the beginning point, the start point. You still have to calculate it. Okay? In other words, if you want to use the determinant, you want to use this equation, you need to know how to calculate the determinant of a 3 by 3 matrix. If you say, I don't want to deal with the determinant of 3 by 3 matrix, for some reason I didn't do a good job in linear algebra, that's not the problem. For this class, you go back to look at this. You do the cross product by yourself. And that's the typical way I do. Okay, so it's not a problem, just in case you don't know how to deal with the determinant.